One measurement was supposed to settle one of astronomy's oldest questions. Instead, it did something no one expected. It broke one of the most trusted predictions about how the universe should behave. At the time, astronomers weren't searching for a mysterious new force. They weren't trying to rewrite cosmology. They believed they already understood the bigger picture. The universe had been expanding since the Big Bang. Gravity should have been slowing that expansion ever since. Only one question remained. How much had gravity slowed it down? Around the world, larger telescopes, more sensitive digital cameras, and years of patient observations were all aimed at answering that single question. Every calculation pointed toward the same expectation. The universe would keep expanding. Gravity would keep slowing it down. No one expected the prediction itself to fail. Then the measurements began to arrive. One by one, they landed in the wrong place. Not wildly wrong. Not randomly wrong. Wrong in exactly the same direction. At first, the simplest explanation was that something had gone wrong with the observations. That assumption would not survive for long. Because over the next 2 decades, entirely different instruments, studying completely different parts of the universe, kept arriving at the same impossible result. The investigation was no longer asking how much gravity had slowed the universe. It was asking whether gravity had ever been enough to explain it. For decades, that should have been the end of the story. Gravity pulls matter together. The universe contains an unimaginable amount of matter. So over billions of years, gravity should slowly win. Not enough to stop the expansion overnight, but enough to make it lose a little speed, century after century, galaxy after galaxy. That prediction was so widely accepted that entire observing programs were built around measuring it. The question was never whether gravity was slowing the universe. The question was simply, by how much? To answer it, astronomers needed objects bright enough to be seen across billions of light years, and reliable enough that their true brightness could be calculated before anyone looked through a telescope. Those objects already existed. They were a rare kind of exploding star, called a Type 1a supernova. For a few weeks, one of these explosions can outshine an entire galaxy. Once astronomers corrected the shape of its light curve, they could predict how bright the explosion really was. Compare that true brightness with how bright it appeared from Earth, and the distance could be measured with remarkable precision. Then one more measurement completed the picture. The light from that same explosion had stretched as it crossed the expanding universe. The farther the light had traveled, the more it had been stretched. That stretching revealed how much the universe had expanded since the star exploded. Distance. Expansion. Plot enough of those explosions on the same graph, and the history of the universe should begin to appear. The prediction had already been drawn. Nature only had to answer it. Then the first distant supernovae appeared on the graph. The prediction should have become clearer. Instead, no better. It started falling apart. The first reaction was not excitement. It was suspicion. Extraordinary claims have a long history of disappearing once someone finds the mistake. Perhaps the distant explosions were hidden behind cosmic dust, making them appear fainter than they really were. Perhaps stars billions of years ago exploded differently from the ones astronomers used to calibrate their measurements nearby. Perhaps one telescope had introduced a subtle bias that no one had noticed. Every one of those possibilities had to be taken seriously, because if even one survived, the investigation would end there. Researchers returned to the data. They recalibrated cameras. They compared observations from different telescopes. They tested whether dust could be stealing just enough light to fool the measurements. They examined whether the exploding stars themselves had changed over cosmic time. Instead of shrinking, the contradiction remained. Then something even more difficult to dismiss happened. A completely independent research team, using its own observations, its own analysis, and its own methods, reached the same conclusion. The distant supernovae were consistently dimmer than a universe slowed only by gravity allowed them to be. Two investigations had begun from the same prediction. Neither had been trying to overturn it. Yet both had arrived at the same place on the graph. The anomaly was no longer a single result, waiting to be explained away. It had become a pattern. Even then, astronomers refused to call it a discovery. One question still stood between an uncomfortable measurement and a rewritten picture of the universe. If these exploding stars were telling the truth, could an entirely different way of measuring the universe arrive at the same answer? The next evidence did not come from exploding stars. It came from light that had been traveling through space since the universe was less than 400,000 years old. Long before galaxies formed, the young universe was filled with a hot, glowing plasma. As that plasma cooled, it released a faint glow that still surrounds the entire sky today. Space observatories mapped that ancient light with extraordinary precision, not to search for the strange result seen in the supernovae, but to answer completely different questions about the early universe. When researchers finished comparing those maps with their measurements, another piece of the investigation quietly changed. The geometry of the universe appeared to be remarkably flat. That alone was not the surprise. The surprise came when they asked what was making it flat. The amount of matter measured across the universe was nowhere near enough. Galaxies, stars, gas, dark matter. Add them together, and they still fell far short of what the observations required. The missing piece was enormous, and it behaved nothing like ordinary matter. The investigation had reached a place no one had expected. The supernovae had suggested that gravity alone could not explain the universe's expansion. Now, an entirely different observation, looking back to the earliest light in cosmic history, was pointing toward the same conclusion from the opposite direction. The contradiction had survived a completely different experiment. But there was still one way out. Perhaps both methods shared some hidden weakness that no one had recognized. That possibility lasted only until astronomers began drawing a map unlike any they had ever attempted. Instead of measuring exploding stars, or ancient light, they started measuring the positions of millions of galaxies spread across the observable universe. The idea sounded almost impossible. If the universe had expanded in a particular way, traces of that history should still be written into where galaxies ended up. Not as obvious patterns, not as giant cosmic lines stretching across space, as a faint statistical preference. Across hundreds of millions of light years, galaxies should be just slightly more likely to appear at one particular separation than at any other. It was an ancient fingerprint left behind when the universe itself was young. Survey after survey began measuring it. Not thousands of galaxies, millions. Each one became another point on an enormous three-dimensional map stretching across billions of light years. No exploding stars. No ancient afterglow. Just the present-day structure of the universe itself. When researchers compared those maps with the expansion history suggested by the supernovae and the early universe, the investigation changed again. The same expansion curve kept returning. Built from different instruments, different observations, different periods of cosmic history. Yet every path led back to the same reconstruction. The result no longer belonged to one experiment. It belonged to the universe. By this point, the original question had quietly disappeared. No one was still asking how much gravity had slowed the expansion. The observations had already answered that. Gravity had slowed the universe for billions of years. Then something changed. Roughly 5 billion years ago, the expansion stopped losing speed. It began gaining it. The recurring curve that had opened this investigation returned once more. It was still the same graph. The same axes. The same measurements. Only now, its meaning had completely changed. It was no longer testing a prediction. It was recording a fact. The investigation that began with one unexpected measurement had become one of the most thoroughly cross-checked conclusions in modern astronomy. Only one question remained. If gravity was no longer in control of the universe's largest-scale future, what was? By then, astronomers had stopped arguing about whether the expansion was accelerating. The evidence had become too consistent. The investigation had moved somewhere more difficult. What exactly was producing the effect? The observations could measure what the universe was doing with extraordinary precision. They could not yet explain why. Modern sky surveys continued adding millions of galaxies to the map. Space observatories refined the universe's expansion history. New instruments measured the same cosmic story with smaller uncertainties than ever before. The picture kept becoming sharper. The explanation did not. When researchers combined every major observation, an unexpected inventory of the universe emerged. Everything we can directly see, every star, every planet, every cloud of gas, every galaxy, accounted for only a small fraction of the total. Even after adding dark matter, the numbers still did not balance. Something else dominated the universe. It did not gather into galaxies. It did not form stars. It revealed itself only through the way the expansion of space changed over billions of years. Only after decades of independent confirmation did astronomers give that unknown component a name. Dark energy. The name did not explain the phenomenon. It simply acknowledged that something real had been measured, even though its physical identity remained unknown. Today, observations indicate that this unseen component makes up roughly 68% of the universe's total energy budget. Its behavior is measured so consistently that modern cosmology can predict the universe's large-scale expansion with remarkable accuracy. Yet the simplest question remains unanswered. What is it? Is it a permanent property of space itself? Is it something that changes over cosmic time? Or is it evidence that our understanding of gravity eventually breaks down across the largest distances imaginable? The observations do not choose between those possibilities. They only trace the same expansion curve. Again. And again. And again. The investigation that began with a single measurement ended by separating two ideas that are often mistaken for one another. Measuring a phenomenon and explaining it. Humanity has done the first with extraordinary success. The second remains unfinished. The same expansion curve that once represented a confident prediction now stands as one of the most precise records ever assembled of something we still cannot identify. The graph never changed. Only our understanding of what it was showing did. There was no photograph of dark energy. No instrument ever captured it directly. No telescope has watched it flowing through space. Everything humanity knows about it comes from the same source. its consequences. That distinction matters. Throughout this investigation, every major piece of evidence came from a different direction. Exploding stars measured how distant parts of the universe moved over time. The oldest light in the cosmos revealed the universe's overall geometry. The distribution of millions of galaxies preserved a giant cosmic ruler stretching across space. None of those observations depended on the others. Yet each one kept returning to the same expansion history. Not because scientists chose that answer, because every independent measurement kept eliminating the alternatives. Future observatories will push those measurements even further. They will map more galaxies, observe more distant supernovae, measure the expansion of the universe with greater precision than ever before. Perhaps one of those observations will finally reveal what dark energy actually is. Perhaps it will show that our understanding of gravity must change. Or perhaps it will point towards something no one has imagined yet. For now, the investigation remains exactly where the evidence leaves it. The universe is expanding. That expansion is accelerating. Multiple independent observations agree. The physical cause does not. The graph that once represented confidence now records uncertainty with extraordinary precision. It is one of the clearest measurements in modern science, and one of its greatest unanswered questions.